Recording in progress.
Yeah, comes on everyone. Let's start off. The last thing we have started with gravitation. Hope everyone has gone through the formulas. And like I keep saying, if your electrostatics formulas are good, then your gravity is good. So let's go ahead. So last thing that we did was the space elevator. Other scans on? Perfect. Let's go ahead with one more problem. We got a planet here of mass m and radius r. From very far, there is a comet which is going with speed u horizontally. The perpendicular distance from the center to the comet is a. Now, as the comet gets closer, right, what will happen? It gets attracted towards the planet. So there is a possibility, right? So this would come and crash into the planet. But let's say if you go little fast, then maybe you will crash here. If you go little fast, then you will crash here. If you go fast enough, you can escape the planet. You will miss the planet, right? So the question is find the minimum speed of the comet so that it does not collide with the planet. Okay, don't worry about writing the question stuff. Solve the question. You'll get the PDF anyways. So focus on solving, understanding, and listening. That's where we spend our time. Initially, it is very far. So as it starts approaching the planet, it gets attracted more and more strongly. So find the minimum speed of the comet so that it misses the planet. Comet from very far is attracted by the planet. This is what actually happens with Jupiter. It attracts most of the comets, in that asteroid belt, and the asteroids, and the Earth is kind of saved actually because of that. Or else we would have got bombarded by multiple by now. So comet from very far is attracted by a planet. So find the U minimum so that it doesn't collide with the planet. Yeah, hope the question is clear. Give it a try. Obviously, ना रे यार ये क्या पूछ रहे हैं question? Planet is fixed. तू भी ना. Let's not move the planet. I hope the question is clear. Anyone not clear with the question, please ask me. Now, if I have to do this question, I'll tell you something. See what I think, okay? And this is something I keep telling you every time. Tell me one thing. Do you think this will go in a straight line? Do you think it will go in a straight line? No, right? Do you think it will go in a circle? No, right? And then I keep telling you some statement. What? If you're not going in a straight line, if you're not going in a circle, there's only one way to solve the problems. Conservation of angular momentum, conservation of energy. How do we handle that? Give it a try. I'll give you a minute or two. Yeah. Find the minimum speed of the comet so that it doesn't collide with the planet. It's a decent mains level question. Not something. It would be a little higher side on the mains, and for advanced, it is an easy question. At least get me the equations. You'll still get a decent answer though. And others do keep your cams on during the session. I'll be removing you from the classroom if your cams are not on. So yeah. That looks right, Arya. Anyone else? You got an answer? You can type in the chat box to the co-host. Please do type your answers. That's a good way to know. Arya, can you find the angle of deviation? That would be a deadly question. That would be like really advanced question. If they ask you for the angle of deviation when you miss the planet. Okay, let's see. Listen, everyone. So one thing is clear. Let's say if the comet ka speed was zero, what would have happened? If the comet ka speed was zero, you would get straight attracted to the planet and you will go like this. If you go really fast, then what would happen? You will miss the planet like this. That means when you go with the minimum speed, you just miss the planet. Meaning, if you look at the trajectory, it would look something of this sort. You will go and you will just graze the planet. You will just graze the planet and then you'll fly off. This is how the path would look like. So this is my state one. This is my initial state. This is my final state. So when you're grazing the planet, let the speed be v. This would be the perpendicular distance r. Since there are no external forces on the system, energy is conserved. So initial energy is equal to final energy. Initial energy half mu square. The kinetic energy, potential energy is 0 because you're very far. Final kinetic energy half mv square. Potential energy minus g m small m by capital R, the potential on the surface. This is your equation 1. Since the gravitational force is always passing through the center, because see, no matter where the comet is, the force is always toward the center. If the force is always toward the center, then the torque about the center of the planet is 0. Torque about the center of the planet is 0. Therefore, angular momentum is conserved. What is angular momentum? M into U into perpendicular distance. So even though it is very far, I don't want this distance. I want the perpendicular distance, which is this distance, which is still A. That will be MUA, and the final is MVR. So this is your equation 2. Take V from here, which is UA by R, and dump it in this equation. Small m goes off, you end up with U square by 2. This is V square, which is U square A square by 2R square minus GMM by minus GM by capital R. You solve this, you end up with U is equal to root over 2GM by R 1 minus A square by R square minus 1. That's your answer. This is your minimum speed. If you go anything slower than this, you're going to crash into the planet. So solving, you can check it out. So once you got the angular momentum, you're done. Right, Anvita? Right, Utsa. There, we have 3 people who got the answer. But everyone else got the process. So this is something you need to know, See, no one will, these are not concepts that you have to use angular momentum and energy. When you do a lot of problems, right? And when you keep seeing this kind of patterns, you realize, okay, this thing is not going in a straight line. Okay, this thing is not going in a circle. And the only way I could have solved these problems till now was angular momentum and energy. Once that clicks, the question, after that it comes. Any doubts on this? Clear? Let's see one more. We got a planet and you have a tunnel along a chord. In electro, we did along the diameter. So, but this is a tunnel along the chord. This is the center. So we have a thin tunnel along the chord. The perpendicular distance from the center is d. The mass of the planet is capital M and radius r. You have taken a particle small m and you release from rest into the tunnel. Right. So, and let this distance be x. So x is the distance from the center of the tunnel. We will assume it is a smooth tunnel. So the first part, find the time taken to reach the other end of the tunnel. So if you drop this particle, in how much time will you reach the other side of the tunnel? B part, plot normal reaction. So when this thing is falling inside, right, it actually doesn't, just fall straight. It will actually graze on the tunnel. It will hit the walls of the tunnel and then it will, slide on the tunnel ka walls. So plot the normal reaction on the particle versus X graph. So this will just not be in the air. The gravity will be towards the center. So it will be hitting the walls of the tunnel and it will glide on that. So yeah, find the time taken to reach the other side of the tunnel and find the normal reaction. Let's call this thing 7A. Let's see how do you handle this. Alpha. What alpha? That is d ray. D is the distance between the center and the center of the tunnel. So if you change the value of the d, the position of the tunnel keeps changing, isn't it? If d is 0, tunnel will be in the center. It becomes a diameter and so on. Right, Samya. Got the time right. Okay, let's see. Can you get the value, Samyak? Right, Utsaha, got it. Let's So let's draw the free body diagram, right? Let it the particle be at a distance x. So this is your tunnel. Let the particle be somewhere here, the red dot. And how will the force be? The force will be towards the center of the planet, isn't it? That would be G-M-M-R by R cube. I hope you remember how we got that. It is basically mass into field. And what is the field inside the solid sphere? Gm small r by R cube. It's a linear function. So that's the field inside a solid sphere. You should know your results. This distance is d and this distance is x, right? So small r is nothing but root over x square plus d square. That's the distance between the particle to the center. And let this angle be theta. So the force acting on the particle would be F cos theta. This is responsible for your acceleration, ma. So F will be Gm r cos theta by r cube. But what is r cos theta? R cos theta is x. So that will be Gm x by r cube is equal to minus acceleration. So this is a is equal to minus Gm by r cube into x. And this is looking like an SHM equation. This is your omega square. Therefore, the time period is 2 pi by omega, which is root over r cube by Gm. This particle actually oscillates in SHM. This thing keeps going up and down, right, in SHM. But I'm not asking you for this. I want you to find the time only from to reach the other end. So if you're going from A to B, then time taken to go from one end to the another end is only half of the time period. That's pi into root over r cube by Gm. So this particle will oscillate in SHM. And the best part about this answer, it is independent of D. That means it doesn't matter where you dig the tunnel, you're going to get the same answer. The answer was independent of D. You can dig the tunnel in the center, corner, you can make the tunnel small, big. As long as it is a chord, you get the same answer. This is independent of D. And what about the normal reaction? Just to draw the FBD again, if you look at the tunnel and if you look at the forces, this is the gravitational force, which is G m small r by r cube. The normal reaction on the tunnel will be this way. This angle was theta. So the normal reaction N is G m m r sine theta by r cube. And what is r sine theta? D. That is G m m d by r cube. Interestingly, you get a normal reaction constant. So they could actually play like this, they could say the tunnel has a friction coefficient of mu and then it is sliding inside. You'll get a constant frictional force. You can actually play something like that. So if you try to plot a graph, you get a constant line. The tension, normal reaction is constant. This will be a pretty good, multiple choice question. So if you try to plot a graph between normal reaction versus X, you end up with a constant line. Please have a look at this. Quite a useful thing. So the time period doesn't depend on where you dig your tunnel. So it's just a chord. Any doubts on this? Clear now, yeah? Shreyan? Shreyan, clear with this? Tanishka? Ashvi? Clear? Srihari? All clear? Now, based on this, let's see how to make this even better. What if you dig a tunnel like this, an equilateral triangle? I know, they have gone mad and they started digging tunnels like this, let's say. These edges are smooth, so you're not going to collide, you will just glide anyways. Equilateral triangle, this the radius of the planet is r. The particle is released from one corner. So let's call this thing A, B, C. Equilateral triangular tunnel. Find the time period for one rotation. You have to start at A and come back to A. Find time taken to go from A to B to C to A. Let's get this. It looks scary, yeah? It is nothing. Just think carefully, you'll see it. Hmm. Hmm. Right, Arya. Right, Samyak. Others, think. I'll give another 30, 40 seconds. See if you can figure out. This and the previous one are same. Okay, let's see who else. Srihari. Ne Srihari, that is wrong. That we'll see later on. Nere Utsa. Chalo, listen. Forget about the triangle. The triangle is just a, decoy. It's nothing to do with this. Just now we proved, independent of where is the tunnel, the time period is same, isn't it? So can I say AB is simply a chord independent of the tunnel ka position, the time period is same. So time taken to go from A to B must be simply the same time which you got from here, which is pi into root over r cube by gm, which is proved in part 1. So you're done. So you want to find the time from A to B, that is one chord, plus B to C, that is the second chord, C to A, that is the third chord. So this is simply 3 times pi root over r cube by gm. It really doesn't matter where you build the triangle. You could even made a square inside. Then what is the answer? 4 times. You could have made an hexagon 6 times because each one is a chord, isn't it? Each side is a chord. And it doesn't matter the size of the chord. It doesn't matter the distance of the chord. So yeah, it works. Clear? That looks easy, no? But yeah, you need to know the first part though. Let's see something even better. Someone decided to dig a tunnel like this. That is your center, huh? I didn't draw it properly. This is x is equal to a, this is x is equal to r by 2, this is x is equal to minus r by 2, and this is the tunnel there. So this is a, this is b, this is center, this is d, and this is e. Time taken to go from a to b. You released a particle from here. These are smooth curves, huh? So you're not going to collide. The particle will come, will glide, and will go. So neglect any sharp points or sharp collisions. So these things are smooth curves. You're just going to glide. This is a particle released from rest. So this is just one question. We're just playing with the tunnels here. So I'm keeping all of them together. And time taken to go from A to B to C to D to E. Let's see how will you do this. Nere aa rahi hai. Now you're guessing. Do it properly. This looks like the previous one. It is not. So be careful. Take a minute or two. Figure it out. Okay, let's see. Got something. Samyak. Okay, Samyak got something else. Arya got 2 by 3. Samyak got 4 by 3. One of you is wrong. Others should keep trying. You got a minute more. I want you to try. It's completely fine to get a wrong answer. Completely fine to mess up the whole thing. But try. Yeah, but if someone has problem with their hair, they have scratching the hair, that is also okay. But keep thinking and solve the problem. You can continue scratching your hair. That's completely fine. It's allowed. Srihari also got 4 by 3. Interesting. Mm-hmm. Okay, should I show you? Think of like this. Is AB the full chord? AB is not the full chord, right? CB and this thing, let's see. Okay, let's check it out. Let me just, split this whole thing into pieces, okay? So that it'll be more easy for us to observe. So let me just draw A to B ka tunnel. So A to B. Now understand, if this had been a full tunnel, this is how it would have looked. So from A to B, this would be simply how much time? Half of the 1/4 of the time, isn't it? This is T by 4, where T ka value is 2 pi root over R cube by GM. This is the total time period for a tunnel, which we proved in this case. So this capital T is the time period for one oscillation in a full tunnel. Now, you're mixing up SHM here. So you're going only one half of an oscillation. So from here to here, it is T by 4. Great. The horizontal tunnel. Now, when you're going from x is equal to r by 2 to x is equal to minus r by 2, you guys remember in SHM, how much time does it take to go from 0 to a by 2? In an SHM, the particle takes how much time to go from 0 to a by 2? T by 12 and T by 12. Hope you guys remember that. Because see, the end of the day, the particle will think this is a part of an SHM, isn't it? If you had a tunnel till here, that would have been a different story. So the motion starts from somewhere in the middle of the tunnel. So you have to go from here. And then when you're coming down, again, same story. This is the tunnel there. You're going from D to E. And this would be again a 1/4 of an oscillation. This is T by 4. There. So your total time will be T by 4 plus T by 6 plus T by 4. That would be T by 2 plus T by 6, which is 2 by 3T. And T is nothing but 2 pi. So that's 4 pi by 3 root over R cube by GM. Have a look at this. See where it went wrong. See how you got 5 pi by 3. It should be 4 pi by 3. Any doubts on this? Clear, na, Anvita? Got your mistake? Aditi? Clear with this? Advait? Advait, clear? Devanshi? Ishman? Clear? It's a good one. Let's still go further. See, that's how you play with a question. Huh? You take one and you just play with variations in this. That's how they do in advance. Like it's not like your mains, where they'll ask you one simple concept and they're just playing around with this. So again, we got a planet here, mass m, radius r. We have a tunnel along the diameter. But this time, you're not going to release it, but instead you're going to throw inside with a speed v, which is root over gm by r. Particle m is thrown into the tunnel with a speed of root over. Find the time taken to reach the other end. So this tunnel problems in gravitation, right, are a mix of simple harmonic motion. So it's a pretty good set of questions. Let's see how you handle this. Any ideas? Let's see. You get a very beautiful answer. Just give me a minute. Yeah, let's see this. Okay. So think of like this thing, huh? You're projecting with u is equal to root gm by 3r. So one thing is clear, right? Once you're inside the tunnel, it is still an SHM. I hope that is everyone agrees with that statement. Because once you're inside the tunnel, the force is still gmm by r square. Everything will look the same. Now, for this particle, what it feels? It will feel, okay, I'm doing an SHM, but I'm not starting from the extreme position. Isn't that what it feels? I'm doing an SHM, but I'm not starting from the extreme position. So this thing will think, okay, I'm starting somewhere here. And this was the whole thing here. And it was like this. So this was x is equal to 0. This was x is equal to r. And this was your x is equal to amplitude, the extreme position. So if this had been a complete SHM, this is how the whole thing would have looked like. And you're saying at this point, your speed is u is equal to root over gm by r. Is this logic making sense? How we can interpret this? Forget about the planet, forget about everything else. If you just look at the particle perspective, it feels as if, it's a big tunnel of the two-way, right? Maybe there's a big planet. And when you start from rest from that planet, so when you reach here, the speed is this thing. And then we know in SHM, there's a very useful formula, omega into root over a square minus x square. So if I use this, so the speed is root over gm by r. And omega is nothing but gm by r cube. And this is nothing but a square minus r square. Omega, where did I get from? You got it from part 1. This is your omega, gm by r cube. And when I do this, gm by r, everything gets cancelled out. You end up with a is equal to r root 2. That means your amplitude here is r root 2. Or you can say this is nothing but a by root 2. So indirectly, the question has become, find the time taken to go from a by root 2 to minus a by root 2. Isn't that the whole question now? Is that making sense, everyone? So for the particle, it will feel, okay, I am doing an SHM, but I'm not starting from the extreme position. I'm starting from somewhere in the middle of the SHM, right? So yeah, and once you get that, you're done. So what is the time taken to go from here to here? So the whole question has become like, going from here to here. So this would be t by 4. Hope you remember that. And this is t by 4. T by 8, I'm sorry. T by 8 and t by 8. In case you forgot about these things, please go to SHM notes. You should definitely refer that. You can't keep forgetting things. This we did in basics here. There. Hope you guys remember this thing. Times 0 to a, t by 12, 0 to a by root 2, t by 8, 0 to root 3 a by 2, t by 6, and 0 to a, t by 4. You should know your time intervals. And then you're done. So the time taken to go from the time, this thing, is t by 4, and then you're done. So that's pi by 2 root over r cube by gm. All clear with this? Yeah. You can use the potential at A and get the speed. You can do a lot of ways, but this thing I found it faster. Like you can use that speed curve formula and get the amplitude. So this whole equation becomes as if you're traveling in an SHM from a by root 2 to minus a by root 2. Clear? So all these 4 problems are a part of one model. So tunnel problems. And this all the tunnel problems are based on SHM only. So you need to understand that. So it's mostly in SHM. A gravitation is just there like a side dish. That's not the main one. Great. Let's see one more tunnel, but a little different one though. So we got a planet. We got a tunnel till the center. Now what you did, you took a rope and you placed the rope inside. Yeah, that's a rope. So we got a rope of linear density lambda. What is lambda? Mass per unit length. of length r/2 is held at rest by an external force. If you leave it, it is going to fall into the tunnel. So someone is holding the rope with an F external. Planet ka mass is m/r. The first question, find the external force. The second question, find center of gravity, not center of mass. Hope you guys remember the difference between both of them. Center of gravity is the point where the net force seems to act. Center of gravity of the rope. So the formula for this thing is there. So this thing is not there in the portion. So mostly they would give you a small explanation here. Center of gravity is given by integral r df by integral df. Look at this thing. If your gravity is constant, then df becomes mg, right? If gravity is constant, df becomes dmg and integral dmg. Gg will cancel, you'll get integral r dm by dm. It becomes center of mass. Let's get this thing. Find F external and center of gravity. Advai, please give it a try. Everyone should stop playing with their hair until unless you have some kind of lice problem in your ear or something. Like, don't keep scratching your hair. Like, I don't know why you guys are doing that. Focus, solve the question. You're scratching with one hand. I can still understand. Who scratches with both the hands like this in the middle of the class? Seriously, let's get this. In case someone has that feeling like, oh, online class, so kuch bhi karenge chalega, then I think you're in a wrong place. Let's get the F external. So yeah, that's manageable. Gm lambda by 2. You got an answer without R. That's interesting. Nay, Param, that is wrong. What is L? L diya na? R by 2.
So L is lambda.
Okay. G3G by 4R. Let's see. Did you take limit 0 to R? Yeah? No, right. Hmm. Right, Anvita. Right, Samyak. You have to integrate because the field is not constant. You have to integrate for each section and then we have to add it up. So this is how we start. At a distance x from the center, take a small piece dx. So the force on the small piece dx will be the mass dm into the field at that point E. The mass dm is lambda into dx. And what is the field inside a solid sphere? G capital M, the distance x by r cube. So you want the net force. This will be integral G capital M lambda by r cube. That would be x dx from 0 to r by 2 to r. That turns out to be, that would be r square by 2. Substitute here. That will be 3gm lambda by 8r. There. Have a look at your answer. Any doubts on this? That was easy, right? That was your force. And what do you want to find next thing? You want to find the center of gravity, and it is given, the formula is given. So the center of gravity it is integral r df by integral df. So here r is nothing but x, and df we have already calculated here, gm lambda x dx by r cube. Limits will go from r by 2 to r. Denominator integral, again df. Df is this term, everyone. G lambda x dx by r cube. Limits will go from again r by 2 to r. That gm lambda r cube, everything will go off, and you end up with integral x square dx by integral x dx. Limits goes from r by 2 to r and r by 2 to r. That would turn out to be how much? R cube, this thing 7, r by 9. That's your center of gravity. It's more closer to the surface because kind of expected, right? There is more force on the other surface. Center of mass would be 3r by 4. Right, Utsa. Got it. Any doubts on this? All clear with this? So solid spheres, you can play like this. So we have more variations, but I will see it later on.
Sir,
Huh.
sir, what I did was like I took the total force which we got and equated it to G M M by x squared.
No,
So
you
इससे
can't do
आंसर
that.
रॉन्ग
See,
क्यों आता है?
आता है answer wrong. Center of gravity is a point, like I said, right? Center of gravity is used to find torque. I told you last time also this. Look at the formula. It looks like RDF. That's a torque ka term. That's not force ka term. Isn't it? COG is like a point. If you apply force at that point, you balance the torque. Mathematically, if you see, that's what it feels like, right? So you can't take that point for force.
Okay,
Next
sir.
thing. Yeah. Now, like I said, right, there are more models on solid sphere, but we have done them in electro, so we are not repeating those things again. We will focus here on the things which we didn't do there. So, but I hope you can see the resemblance. The next thing, acceleration due to gravity. Now, what is this acceleration due to gravity, right? We keep saying G is 9.8, you know, the gravity on the surface and all this stuff. So what is it that you're exactly experiencing? So if you go and stand on the surface, you experience a force of technically G m small m by r square. That is a force you experience. And this is what we started calling as gravity. So the force is nothing but mass into field, and you're calling this is m into g. So indirectly, the acceleration due to gravity g is nothing but gravitational field. In electrostatics, it was force per unit charge. Here it is force per unit mass, which is same as the field. So the gravitational field at a point is simply the acceleration due to gravity at that point. But anyway, most of the time we talk about surface. So the gravity on the surface is given by gm by r square. That's your value. If you want in terms of density, then this will be g into rho 4 by 3 pi r cube by r square. So sometimes they'll give the density of the planet instead of mass. This is the relation between them. So if you substitute the value of all this stuff, you'll get the acceleration due to gravity for the planet. If you substitute the mass of the Earth and radius of the Earth, the value for the Earth comes out to be 9.81 meters per second square. If you do the same thing for the Moon, you get 1/6 of the Earth ka gravity. That's around 9.81 by 6 meter per second square. If you do this for Jupiter, again, no need to remember these values I'm just giving. Jupiter ka value comes to around 62.1 meter per second square. So if you go to Jupiter, your weight is almost 6 times more. And that's what happens, when these people launch some satellites or some rovers onto the planets like Jupiter and Saturn, right? So they are taking care of the average density area. Technically, the planet density will vary everywhere. We're not going to deal with that. And think about it anyway, right? The particle on the surface doesn't care what is the density here. End of the day, it matters on the total mass. So what you're taking here is rho average. Yeah. That way, you can play around like this. So if you don't design a rover based on that, the moment it lands, it'll get crushed by the planet gravity, and you're gone. Your entire journey ka time is wasted. Now, what happens if you try to find this with height? What if you go above the planet and then we want to see how does the gravity vary? The variation with height. So if you take a planet, if you have a particle m, and let's say you're at a height h, like I said, the same thing, m into the g apparent. So this is your apparent gravity. Is nothing but mass into field. So G apparent will be Gm by R plus H whole square. Take out R square common. You get 1 plus H by R whole square. And what is Gm by R square? The G on the surface. So the apparent gravity. So when you go to a certain height H, the gravity there is the gravity on the surface divided by 1 plus H by R whole square. Okay, that's a pretty good formula you need to remember. Now, in some cases, what happens, they will say you're at a height of 10 kilometers, you're at a height of 20 kilometers. So the height is much, much smaller. If your h is much, much less than r, like example, if you look at the radius of the Earth, it's 6,400 kilometers. And let's say you're taking height is 100 kilometers. So yeah, it is small. Then we can approximate the formula with the binomial approximation, which is g apparent into g surface. So when this guy goes into the numerator, it will become 1 minus 2h by r. So be careful. Use this formula only when the heights are small. If the heights are comparable to the radius, don't use this. If this is a 10 kilometer, 20 kilometer, use this. So that's your approximate formula there. The second variation is variation with depth. So if you go into the Earth, let's say you go in deep depth d, then from the center, this distance will be r minus t. So G apparent is nothing but field. And what is the field inside the planet? Gm x by r cube, which is Gm. X is the distance from the center. So r minus d by r cube. So we get G apparent will be G into, which is the surface, into 1 minus d by r. Here there's no approximation. This is the perfect formula. This is the exact one. So when you go with height, there is an approximation. Yeah. You can note it down in case you don't remember them. Clear with this? So that means, on a planet, the gravity is maximum on the surface. So if you dig a hole into the Earth, the gravity drops, right? If you go above the surface, the gravity again, drops. Right? Let's see. The third one, this we have done in circular motion, if you remember, variation with rotation. So because of the planet rotation, the centrifugal force, right, it feels the gravity has decreased. This we did discuss in circular motion in detail. This one, if you guys remember, variation of acceleration due to gravity. Remember this? So if you're standing somewhere at a theta, right, you're going in this horizontal circle, the centrifugal force will be m omega square small r. So the free body diagram of the person would be this. So m omega square r ka horizontal component, the what component will be m omega square cos theta, and then you end up with this. So this was the whole stuff. So I'll just put it down from here. These are the three variations you should know. Have a look at this. So the planet rotates fast enough, the gravity drops. If you go above the planet, gravity drops. If you go into the planet, gravity drops. So on the surface, you experience maximum gravity. Clear? Let's see how they'll frame a question on this. These are pretty good mains level questions, huh? They would ask on this. Find the distance from the surface. I'll keep all of them together. Where G apparent is equal to G by 4. Time period of a pendulum on surface is T. At what height the time period becomes T by 3T. Uh, that is from SHM. A barometer. Remember a barometer? This is from fluid mechanics. A barometer shows 75 centimeters on surface when the atmosphere pressure is P naught. Right? At height 3R. So if you take this barometer to a height 3R, it shows 90 centimeters. Find the pressure at that point. G apparent on surface of the equator is equal to G apparent at a height h above the North Pole. If h is much, much less than small r, we are taking small heights. Find h. There, get them. So these are simple mains level questions. Some of them will be even CET level. So previous slide here, this one. So G apparent for rotation is G minus omega square r cos square theta. Clear with this? Get all four of them, everyone. Try. I'll get another 2 minutes, and I'll show all of them together. Yeah. Some you got it. Others, I'll give another 30, 40 seconds. Get all of them, Maria. Get all of them. Let's see. Okay, let's get all of them. The first one, find the distance from the surface where G apparent is 4. There are two answers. You have to be careful with that. He didn't say height. He didn't say depth. He simply said, find the distance from the surface. And there are two answers. It can be above the Earth's surface or it can be into the ground. So when you take the surface, so I can use G apparent is equal to G by 1 plus H by R whole square. This is G by 4. So this would give you H is equal to R. The other option, G apparent, if you go into the earth, that would be G into 1 minus D by R. That is equal to G by 4. And that would give you D is equal to 3R by 4. Make sense? So if you go height R above the surface, or if you go depth 3R by 4, you get the gravity there. Second thing, the time period of a pendulum is 2 pi root over L by G. That means the time is proportional to 1 by root G. And in the question, it is mentioned the time period has become 3t. Since the time period has become 3t, the gravity must have become G by 9. G apparent is G by 9. So then we use the formula G into 1 plus H by R whole square. And this thing clearly gives you H is equal to 2R. So you should be at a height of 2R from the surface. You can see how you're playing around. So you just need to get that G somehow and see which formula works. The third one, you're talking about a height of a barometer. If you remember the height of a barometer, the formula is H is equal to pressure by rho G. Simple, pressure is equal to rho G H. So H is proportional to pressure by gravity. So initially the height was 75 centimeters, right? The pressure was P naught and rho was rho only and gravity. And now you're saying when you go to a height of 3R, your G apparent becomes G by 1 plus H by R whole square. That is g by 1 plus 3r by r whole square. That is g by 16. So the new height will be 90 centimeter. Pressure, I don't know. That's what I have to find. And the gravity has become g by 16. So this is your equation 1 and this is your equation 2. Divide them. So you end up with P dash by P naught is equal to 75 rho g by 90 rho g by 16. That's 15, 5 by 6, 40, 40 by 3 or 3 by 40. So I think I goofed up somewhere. Yeah, I goofed up. This is 90 rho g by 16. This is 75 by rho g. Yeah, that's 6 by 75. That is 3 by 40. The 40 by 3 by 40 is the answer. Clear with that? 3 by 40. And then the fourth part, you're saying g on the surface of an equator is equal to g apparent at a height h, and h is much, much smaller. So this is what he's asking if you see on the picture. So there is a person who's standing on the equator. There is a person who's standing at a height h. And he's saying both of them feel the gravity is same. So this guy will feel g apparent will be g minus omega square r. This guy will feel since the h is small, we can use approximation g into 1 minus 2h by r. Then equate them. G minus omega square r is g into 1 minus 2h by r. G would cancel. That would be omega square r is equal to minus 2gh by r. Then you end up with h is equal to omega square r square by 2g. Clear with this? So actually using this technique, if I know the h, if I know the g, and if I know the earth rotation, I can find the radius of the earth. You can do a lot of things like this. All clear with this? So that is how they'll ask a mains level or a CET level questions like this. I kept all of them together and G apparent. Take a break. Come back by 9:45. We'll continue from here. Any doubts so far? Then come back by 9:45. Yeah, let's start off. Camps on everyone. Let's see another variation of this. So we got a planet here. The planet here is revolving with omega, which is root over g by 4r. That's pretty fast. Mass of the planet is m, the radius is r, and there is a point A on the surface. So A is a point on the equator. Then, due to internal forces, this planet shrunk. It shrinks to half the radius r by 2. We have done something like this in rotational mechanics. The point A is still on the surface of the equator. So the mass remains same, but the radius becomes half. Find the ratio of G apparent before and after shrinking. So at point A, what was that apparent gravity before and after the planet, shrunk? Others do keep your cams on. Let's get this thing. It's a good one. Like, you have to be careful with the terms, and let's see. Do you guys remember what happens actually? Near Samyak. You got trapped. That would be one of the options. Like I said, be careful with the terms. Where you have seen something like this? The first time you encountered something like this was in rotation, conservation of angular momentum. That was a very straightforward, easy question. I modified that. Look at this. This was a question. When we have a solid sphere of mass and radius are rotating with omega, shrinks to half the radius, what happens? Since the torque external is zero, conservation of angular momentum, I1 omega 1 is I2 omega 2. Omega becomes 4 times. Remember this? So when it shrinks, the omega changes. Omega doesn't remain the same. That is the first change. Hope you realize that. So from conservation of angular momentum, this guy will rotate with 4 omega. So let's call this omega dash, which is 4 omega. That comes from I1 omega 1 is equal to I2 omega 2. The moment of inertia for a solid sphere is 2 by 5 mr square. Omega is 2 by 5 mr by 2 whole square omega dash. So this planet actually rotates 4 times faster. Great. Second thing. So when you want to find the G apparent here, what was the gravity here? This guy is G m by r square. And the centrifugal force was m omega square r. So from here we get mg apparent was G m by r square minus small m omega square r. This is nothing but mg minus omega square was g by 4r into r, and this was 3g by 4. So initially this person will think the gravity has become 3g by 4. This was the apparent gravity before shrinking. Now after shrinking, look at what happened. Number one, omega changed. Number two, the distance also changed. So this distance here is now r by 2. Now if you try to write the forces on point A, look at the forces here. The gravitational force will be G capital M small m by r by 2. The planet is attracting 4 times stronger. Point A is on the surface. Are you getting it? See, it is like this. Initially, A was here. When the planet ka radius became half, A also got shifted here. The point A was not at the same point in space. It actually got closer to the center of the planet. And the centrifugal force, M, omega became 4 omega, that is 4 omega whole square, and the radius became r by 2. So there are multiple changes there, which you have to be careful. So when you try to write this thing as mg apparent, so this is the net force. This would be 4 times g m small m by r square minus this would be 8 m omega square r. This would be 4 small mg, and this guy would be 2 mg. So from here we get G apparent is 2G. So this person will think the gravity got doubled. And now he's asking for the ratio. So that's 3:8. Yeah, you'll get it from there. Is this thing clear, everyone? All the three terms got changed. Huh? The distance became closer, omega changed, the radius changed. If you mess up any one of the term, you get something else. So conservation of angular momentum and then G apparent. Right, Armita? Clear ना हो गया? Arya, Ishman, Tanishka, Utsa. You all need to keep your cams on. Clear with this. So that's a little about your apparent gravity. Next thing, satellites. Now, till this point, right? So if you see the apparent gravity and stuff, this is all not there in electrostatics. So before this, everything was repetitive. Now, all the satellites and all is completely new. We didn't deal with any of this in electrostatics. So satellite. So what is a satellite? An object that revolves around a planet in a stable orbit. Now, what do you mean by a stable orbit? So basically, we're talking about a bounded orbit here. Stable bounded orbit. So what do you mean by bounded orbit? First of all, it should be a closed orbit. Yeah, when you say orbit, it is actually closed. So example, circles or ellipse. These are the things which we deal with most of the things. The total energy must be negative. That is a big definition of a bounded system. Means you need to provide energy to separate them. Right? The derivation is pretty straightforward. So if you have a mass m, if you have a satellite m, it's going in a circle. Let the distance between them be small r. The gravitational force will be g small m by r square. The centrifugal force will be mv square by r. G mm by r square must be equal to mv square by r. This will give you velocity is equal to root gm by r. So this is the velocity, the speed of a satellite at a distance r from the center of the planet. The time period is given by 2 pi r, the circumference, by velocity. So this turns out to be 2 pi by root gm r power 3 by 2. These are some standard formulas, everyone. The time period of a satellite and the speed of a satellite in an orbit of radius r. Please have a look at this. They're not difficult. Even in case you don't remember them, they're always easy to derive. And here, what is capital M? Be careful, capital M is the mass of the planet, not the mass of the satellite. Any doubts on this page? Clear? Aditi? Shaurya? Param? Great. Next thing. Now, if the satellite is very close to the surface, generally, right, launching a satellite very far from the planet, right, is expensive. It consumes a lot of fuel. So what people do, right, most of the satellites, we keep them at a height of 300, 400 kilometers. If you see International Space Station, it is a height of 600 kilometers. Right. So it is like, if you think about this, when the International Space Station is going around the Earth, sometimes you're closer to International Space Station than Delhi. Right. So yeah. It's not exactly on the equator, but yeah, kind of. You can say like sometimes it is closer to the International Space Station than the some other city which is far off. The satellite is very close to the surface of the planet. But when you keep close to the planet, right, you rotate pretty fast. I think you complete almost 7 to 8 times rotation around the Earth in one day. So you won't have access to the satellite 24 hours. So this is called orbital velocity, which is root over gm by capital R. Multiply and divide by R. This becomes gm by capital R square into R. And remember, what is gm by R square? Small g. That's your value there. So this is the orbital velocity when the radius of the orbit becomes the radius of the planet. For Earth, this value comes to around 8 kilometers per second. So orbital exact value something like 7.92 kilometers per second. That's the kind of speeds we're talking at. So if you throw something with a speed of 8 kilometers per second, this will not fall into the earth. This will just keep going round, round, round. But these are really a not, matlab, they have a problem. So if you're going so fast around the planet, right? See, if you have a satellite, this is what it does. Whenever it sends a signal, the signals, right, will always go tangentially. Now, if you're too close, you can clearly see the area which you can cover actually becomes smaller. So the problem is this. So this satellite, you have only access like, in every 4 hours, you'll have access to the satellite for like 1.5 hours or 2 hours. You're getting it? So in a day, there are times when you can't access the satellite. In a day, there are times when you can access the satellite. It becomes a problem. So if you keep it far, you can actually access the satellite for longer time. But if you want to keep it far, it is too expensive. The rocket ka fuel is more expensive than rocket ka parts. So what people do, instead of launching, very far, they launch multiple satellites. And that's what the SpaceX is trying to do. They're just trying to dump a lot of satellites there. Heard about that thing, right? SpaceX ka kya tha? There's a name for that thing. Constellation they're making. They're giving all internet and all that stuff. Forgot the name. Don't know this thing. They can actually provide internet and thing like, when there is a war going on in Iraq, Ukraine, they're actually providing all that internet. Now, when you have all the satellites so close, right? What happens at any point of time, you have access to any one of the satellite. Normally, people use around 24 satellites. We call this in GPS, Global Positioning System. And these satellites are so powerful, especially, right? They use it for military purposes. These satellites have really powerful cameras. The cameras are so powerful, they can look at your car ka plate number. That's the kind of resolution they have. And that is how they detect, if it's actually a terrorist guy or something. And yeah, it's pretty useful to have such kind of a live data. Did you guys see the movie Uri? In that, remember, there is this one scene, this guy says, call up that ISRO, and tell them, like, we need to look at what is this Pakistani terrorist people are doing. Tell them to put a satellite there. And this guy says, okay, we will put one satellite and they give all the data. So if you remember, there was a scene like that. So during Kargil War, right, 1999, Indian Army, right, used to use US ka satellites for GPS. See, because once you go into Himalayas, right, those regions you don't have your internet signals, kuch nahi aata hai. That's completely dark spot. The only way you can communicate is satellite phones. That is the reason India satellite phones are banned. If you go with a satellite phone into a plane, first of all, they'll catch you and arrest you. बाद में discussion होगा. So satellite phones are banned, like because even in Mumbai attack that happened, right? So they actually use satellite phones. So satellite phones you can't track them. You don't know someone is calling or something because the communication goes directly to the satellite in space. So during the Kargil War, what happened? Indian Army used to use this satellites for communication, talking between, there is a battle groups, there is a tanker group, there is an infantry group, artillery, all communications are through this. And US didn't like, we fighting a war. For some reason, they're always mad about it. So India, Pakistan fighting a war, first thing they'll come and jump and say, oh, no war. So Indian said, yeah, you go to hell, yeah. Like, you don't get into every damn thing. They got pissed off. They cut off the satellite communication. During the middle of the war, they just stopped all satellite access. Literally, Indian Army units were stranded in Himalayas. They had no communication network, nothing. And that is when, the government decided, no, yeah, see, no one is going to give us satellite technology, so let's build it on our own. So if you observe something, right, ISRO is one of the world's best satellite launchers. But if you see, DRDO is also a government company, but it never developed the way it should have been. So the thing with us is, what? If someone says we won't give it to you, we'd make it the best. So no one wants to give us a satellite, so we made it the best. No one wants to give us nuclear technology, so we start building stuff. But everyone in the world loves to sell weapons. It's profitable. So the day Indians say, right, we want to make a gun, the US company will come and say, why you want to make a gun? We have the best guns. Take the guns. So, and you get a lot of bribes also. So no one wants to really develop, the weapons in India. You can just buy them from foreign, quote 1,000 crores, and you can take a bribe of 100 crores. So it works out. So there was a story like this, huh? There's this guy, Manohar Parekar, he was a defense minister. He died now. This guy is also an IITian. Right. So this guy, when he became the defense minister, right, first thing he went and started checking, like, where is Indian Army buying stuff from? So Indian Army, right, when they go for these glaciers and everything, when they fight wars in that such cold places, they need special jackets. You can't wear the normal ones. The temperatures are minus 35 degrees. So they need some special boots also. So he inquired, where are these boots coming from? He said, okay, they're coming from Israel. Then he inquired with Israel, boss, where are you getting the boots from? They said they're getting it from a company in Gujarat. Then he asked the army officials, why are you not buying from Gujarat directly? Because we don't know about the quality. But the thing is, the troops, right? When you say, "Arey, ye local made hai," they hesitate. But when you say it is from Israel, they take it. Then they went to the Gujarat company and said, why didn't you sell to Indian Army directly? They said, we love to sell, but they don't buy from us. Then they said, okay, how much you will sell it for? And what is the best part? These people sell it to Israel for X. Then Israel puts the brand of Israel and sells it for 7X. And Indian Army buys it. So anyway, the story goes on like that. So it's important we develop our own stuff. I think that part we are understanding now. So that is the thing. We should tell them like, we won't give you, and then we will develop the best parts. At least that's how it has been so far. Anyway, next thing, the geostationary orbit. What is this thing? So look at the word geostationary, meaning with respect to the Earth, when you look at this satellite, it looks like it is stationary. It's like a fixed point in space. So time period of a satellite is equal to the time period of the Earth. So the time period will be 2 pi root gm small r power 3 by 2. This for Earth we take it as 24 hours. And when you actually calculate the value, this thing turns out to be around 42,000 kilometers. That's the problem. Too far, too much fuel, very expensive. It's cheaper to launch 10 satellites at a height of 200, 400 kilometers than launching one or two at this height. But the advantage of this satellite, you will always have access to the satellite 24 into 7. You can connect a link between, let's say, Mumbai and Delhi, and there is no internet connection through lines. You can get the satellite from internet. But you can also do the same thing by putting 4 or 5 satellites in orbit. Clear with this? And another big problem we have, right? You can't put the satellite wherever you want. There's a huge restriction, not because of some international thing, but physics. The first thing, if you want to put a satellite in orbit, it always has to have the center of the orbit must be always the center of the planet. Yeah. Center of the planet must be the center of the orbit. Why is that? Think about this situation. Let's say if you're putting an orbit like this, and now if you look at the satellite, the gravitational force is towards the center of the Earth, which is gmm by r square. The centrifugal force is away from the center of the circle, which is m omega square r. They are not along the same line. They can never be balanced. These are unbalanced forces. The satellite will collapse, or else you have to keep the engines on 24 into 7. That will finish off all the fuel in few minutes, and then you will just crash. So this is not a good idea there, right? So you have to keep the orbit like this. The second thing, geostationary is even more specific. So first of all, a satellite ka center should be the center of the planet. But if you want to keep it geostationary, it has to be on the equatorial plane. And these are the CD type of questions. Geostationary orbit must be in equatorial plane. That means, technically speaking, there's only one orbit where every country can keep a satellite for geostationary. And by chance, if one satellite goes rogue and it breaks down into pieces, that will literally blast all the satellites in that orbit. So it becomes pretty dangerous. And anyway, we have already polluted the space enough. It's called space debris. And these things, right? The biggest problem is the nuts and the bolts and all. These things fly with a speed of almost 20,000 kilometers per hour. That's the kind of speeds we're talking about. And when they hit at that kind of speeds, nothing survives. So, yeah. So this is the center and this is the orbit. And ऊपर से people love to do all weird things. Like China did it like 5, 6 years back. They had their own satellite whose life was almost getting to the end. So normally what happens, right? When the satellite ka fuel gets over, when it is at the end of its life, the last amount of fuel they have, they use it to direct the satellite towards the Earth, and they crash it in Pacific Ocean. There's a location called Point Nemo. Ever heard about it? That is the farthest point on the Earth from any nearby landmass. I think the nearest landmass was 2,300 kilometers or something. So that's in Pacific Ocean. That's called Point Nemo. So that is also called as, the graveyard of satellites. So that's where they crash all the satellites at their end of the lifetime into that point. But China had some interesting ideas. They said, why don't we launch a missile and hit the satellite and blast it in space? So no, the thing is this, and that thing is going at a speed of 18,000 kilometers per hour. You're sending a missile to track it and hit it. It's not a joke. And they did it. They hit their own satellite with a missile and they proved to the world that we can hit satellites. They're actually giving a signal to US like, boss, you better be careful. We can do this. And then everyone started shouting, oh, China did that, did this, and India did it next. After 2 years, India did the same thing. We also shot down our own satellite and we proved we can hit it. So yeah, it was an interesting game. So that was one thing there. And next thing, right? If you want to cover the whole planet, you need at least three satellites. Satellite one. So basically, the signal will always go tangential. If you can put them in a proper way, right? We need at least minimum three satellites to cover the whole planet. So at any point of time, you will have one satellite access, but you have to keep them at a certain distance. Again, a CD type of question. How many satellites are required to cover the whole planet? That's a bit about the satellite time period and the orbits and the velocity. Next thing, energy. Next class, we will deal with some really good questions of satellite, like advancement. They can really play a lot with this. So what about the energy of a satellite? So if you have the planet and this is small m and you're going in a circle, this is your radius r. So the potential energy of the satellite is minus G capital M small m by r. Hope you remember the formula. G m1 m2 by r. What about the kinetic energy? Half mv square. But what is the velocity? Root over gm by r, which we derived just now. So this thing comes out to be plus G capital M small m by 2r. The total energy is potential energy plus kinetic energy. So if you add them, you end up with minus gmm by 2r. And if you take the ratio, the total energy is to potential energy is to kinetic energy. This is in the ratio of total energy minus 1, potential energy minus 2, kinetic energy is plus 1. Quite an important result, right? This has been in, it's a very standard question. It will pop up in some means, bit CET somewhere. That's the ratio of the energies. And I can also plot a graph for this. If you try to plot a graph versus R, let's say we have a green line, we have a red line, and we have a black line. Can someone tell me which color is which one? Which one is kinetic, which one is potential, and which one is total? So kinetic energy is positive, so the green one is your kinetic energy. Potential energy is more negative, so red one is the potential energy. The black one is your total energy. That's also a question based on graphs. All are rectangular hyperbolas. All clear with this? Yeah. Next thing, escape velocity. the minimum speed required to escape from the surface of the planet. So if you launch something with speed v at an angle theta, so this thing goes off to infinity. This is your state 1, infinity is state 2. Since you're asking for minimum speed, meaning when you reach infinity, you almost go with zero speed, right? It need not go in a straight line here because you're throwing at an angle. So energy in state 1 is equal to energy in state 2. So energy in state 1 would be potential energy minus gmm by r. Remember, this is not a satellite, so don't use that gmm by 2r. Satellite meaning the thing which is going in an orbit there. Kinetic energy half mu square. Since you go to infinity with a zero speed, 0 and 0, so you end up with V escape is root over 2gm by r. Multiply and divide by r, this ends to be root 2gr. And the best part, this is independent of theta, means it doesn't matter at what angle you project. If you throw with this speed, you're going to escape the planet. And for Earth, this value turns out to be around 11.2 kilometers per second, neglecting the Earth air resistance. So if the Earth had no atmosphere, and if you kick something with a speed of 11.2, you escape the planet. Clear with this. And then this thing, right, you can play around a bit more. So if your V escape is root 2 gm by r, if your V escape is greater than speed of light, means what? Even light cannot escape the planet. Meaning if you're standing on a planet like that, whose escape velocity is greater than c, and if you shine a laser into the space, the laser will actually turn back and come back to the surface. It will not go into the space. The gravity is so intense, you pull even the light back, and this would turn out to be r is less than equal to 2 gm by c square. This is called Schwarzschild radius. So that's the German scientist name. Schwarzschild radius. And this is the condition for black hole. So if a star reaches this radius, 2 gm by c square, where m is the mass of the star and c is the speed of light, you get a black hole. Simplistic way of saying, but yeah, this thing makes sense, kind of. And you know how small is this or how dense is this? If you want to make Earth into a black hole, take the entire Earth and put it in a tennis ball. Just imagine that. You take the entire Earth and put it in a tennis ball. Right? And then Earth becomes a black hole. That's the kind of density we're talking about. And generally, black holes, right? We have huge black holes. There are black holes the size of sun or something. Matlab, imagine that star ka size would have been what? So yeah, that is one. Then, Ishman, you're chewing gum in the class. Hmm. Next thing. So if you look at the orbits, look at the trajectories. Yeah, there's a bit of a theory there. Like I said, it's all theory stuff, important. So consider a particle is projected speed v tangentially. So we are taking a very special case. So if you project horizontally with speed u is equal to with u like this, and let's say if your speed v is less than v escape, it's less than v orbit, which is less than root gm by r. This guy will actually go in an ellipse and it will crash onto the planet. This will form an ellipse. The center of the planet will be the focus. So when you're actually throwing into the space, with a really good velocity, you're not actually going in a parabola, you're going actually in an ellipse. And if your speed is less than v orbit, you crash back to the planet. This is the concept of ICBMs, intercontinental ballistic missiles. And I think so far there are like 3 or 4 countries who have ICBMs, like US, Russia, Britain, France. So they can literally hit any country on the earth. We have missiles which can have a range of 6,000 kilometers. So we can hit everywhere in Pakistan and everywhere in China. So I think we don't want to hit anywhere US, at least for now. So that is there. So if you launch this with a speed of v, and if v is equal to root gm by r, you actually go in a circle. So depending on the speed, your shape changes. We don't have in the portion, but actually if you use polar coordinates, right, you can prove eccentricity of the curve using the velocity. For different velocities, you get different eccentricity. Suppose if you project again tangentially, but this time your speed is between v escape, but greater than v orbit. This time you will go in another ellipse, but this time you'll go in a much bigger ellipse. And this time you won't crash onto the planet. So you actually get an ellipse 2 times. What's eccentricity? They didn't teach you conic sections in max yet. Yeah, that's the problem. Let them teach you. So the eccentricity tells you about the curve. So if you project v is equal to v escape, you get a parabola. Now see, parabola is an unbounded curve, so it escapes to infinity. Literally, you're getting all the shapes. Suppose if you project v greater than v escape, these are good theoretical questions. Bits and CET means they do ask stuff like this. And again, it goes off in a curve. This is a hyperbola. There you literally got all your conic sections. Depending on with what speed you're projecting, you can get different trajectories. Okay, let's see one question, simple one. We got a planet whose radius is density is rho and radius is r. This density is 2 rho and radius is 2r. Find the ratio of escape velocity and find the ratio of g on the surface. There, let's get them. Okay. Right, Samyak. Right, Arya. Got the first one. Get the second one. Nere param. The second one is wrong. Okay, let's see. It is just matter of substitution. What is G? G is G capital M by R square. What is mass? Density 4 by 3 pi R cube by R square. So G is proportional to rho into R. So for the first question, G1 by G2 is rho into R by 2 rho into 2R. So this is 1:4. Great. The second one, what is V escape? Root over 2gm by R. This is 2g root over 4 by 3 pi R cube by R. So this is proportional to R into root rho. So V1 by V2 will be R into rho by 2R into 2. Just a formula substitution there, nothing really much to think. Check it out. All clear with this? Any doubts on this? Yeah. Great. So that's a bit of a theory about satellites and all. So next class, when we catch up, we'll continue from here. We are going to do some really good ones. So you have seen Mangalyaan movie, Akshay Kumar ka? Yeah, they did all crap in the movie. They couldn't explain, but we're going to do a literally a problem on that. That what he tried to do in that movie, right? It was actually a simple problem. He messed it up. He tried to make a movie out of it. But anyway, we will see some good stuff. That will be a very good advanced level paragraph, with some stuff and all. So yeah, next class we will see more high level advanced problems based on satellites. Mostly, I think we should be able to wrap up this by another 1.5 class maximum. So after that, we'll start off with Gauss laws. That is a next version of electrostatics. Okay, with that, we'll wrap up for the day. And do remember, there's a test online till tomorrow, so make sure to give it. So, any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you guys again next Tuesday, same time. So, take care, stay safe.
Bye, sir.
Bye.